Hello, today we'll be going over the concept of flood fill, which is a very common graph algorithm for USCO, especially in the bronze and silver contests. Um, yeah, so let's get into it. So what is flood fill? So flood fill is basically, you can imagine it or like kind of conceptualize it as pouring water into a maze, and the water is going to flow into all the connected spaces. It's going to fill all connected areas, but it will stop at the walls and boundary. So if you have something like, oops, um, yeah, I'm not sure. So let's say you just pour water into this figure or whatever you want to call it, then the water is going to fill in every single available area that's connected. Um, so I won't draw on that obviously, but if you have like another maze right here, obviously the water poured in here will not get to here. So you have the important distinction that it's going to be stopped by any boundaries or walls, but it will fill in all the connected areas. So you can tell if by pouring in the water that this point and let's say this point is connected. Let's say if there's like some kind of a boundary right here, then we would know that they are not connected if the water just fills up here, but it's empty right here. So that's kind of like the concept of flood fill. Um, and yeah, you can, I guess, think of it like some real world examples of flood fill would be maybe using a paint bucket tool, um, or even like some game like Minesweeper to reveal empty spaces. But yeah, so in the context of competitive programming, what is flood fill used for? Well, it can be used for finding connected regions, counting components, measuring region sizes, and maybe even like testing connectivity. So finding connected regions, we just talked about that. You can see if one area in the graph is connected to another area in the graph. If, um, I guess, during the flood fill, you kind of color it or you mark it as connected. You can count components by actually finding connected regions and then counting how many individual regions are there. So you might have, let's say, something like a region here, and then you might have, I'll actually just make graphs now, and you might have regions here. So you know that these two are empty. You can, if you flood fill on this, you'll get all of these, but you won't get this, so you'll have this separated. Measuring region sizes. During the flood fill, you can just simply have like a counter or something like that to measure how many nodes are in the connected components. And testing connectivity, if you perform a flood fill on, let's say, the parent node, you want to see if it reaches a leaf node, you can just perform a flood fill and see if it arrives at the target point. So, yeah, in USICO, you'll see a lot of problems with graphs, like physical graphs. Let's say um, you're traveling somewhere geographically, or you're exploring an area, or any of that sort. Those are kind of, I guess, clues that you might be dealing with a flood fill problem. And so um, you might be wondering, like, what's the difference between DFS and flood fill? Well, the key difference is that DFS is kind of like a general algorithm that works on any type of graph, usually with adjacency matrices or lists, whereas flood fill kind of works specifically in 2D arrays and grids. So it's like simulating like geographical, I guess, movement or whatever of that sort. For neighbor definition, so for DFS, if you watch the previous videos, I talk about how you have explicitly defined neighbors, which basically means you have the connected components. Whereas flood fill, you have to just it's like intuitive, I guess, but you have to know that its neighbors or connected components are what's right next to the grid. So, for example, let's say you have a graph like this for DFS. For this node right here, you'll know that these are the connected components or nodes. But for something like flood fill, now I'll draw a graph so that it's more realistic. Okay, yeah, bear with me here. Let's say you're currently at this node right here. This node right here, well, the adjacent nodes you're not explicitly given, but obviously you know you can travel here, you can travel here, you can travel here, and you can travel here. And in some cases you can also travel diagonally, making basically all these nodes, you can think of it as like the connected components. And yeah, so this also determines the movement patterns, in which you see DFS kind of travels along these edges towards its connected nodes, whereas a flood fill will move in, let's say, either 4 or 8 directions. So it'll either be adjacent nodes or also diagonally adjacent nodes. And yeah, I guess just the use cases are that DFS is generally for any type of graph traversal, whereas flood fill is very specific to connected regions within a grid, like right here. So with that out of the way, I'll just talk about some benefits of flood fill algorithms. So flood fill is very simple to implement. And you can kind of intuitively understand how a flood fill algorithm works. Unlike DFS, which is kind of not really, I guess it's a little harder to visualize. Flood fill is just a 2D grid, and you're just looking at the nodes next to it. It's also efficient in memory because you only need a visited array, which I guess a problem might be when your grids become too large, but you only need at most one way to color one array or one 2D array to color which nodes you visited or maybe in some other format. And yeah, I guess these two can also be kind of the drawbacks to flood fill because like I just said, if your grid is very large, so it's like 10 to the 5 x and y, then you'll definitely go over the memory limit. And also, it's simple to implement and very intuitive, but that means it's also limited to just grid-like structures. You can't really, I guess, apply it to all those different graphs like DFS. And yeah, that's basically a brief introduction to what flood fill is. I'll be going over implementation and also practice problems in future videos. But that's it for now. Thank you for watching.